Okay, we're recording. So let me give it over to you guys, and you can present your heliostat project Icarus.
Good afternoon. I'm Bridget Ortiz, and here alongside with me we have Matthew Estenovs, Jerome David, Matthew Lifrig, Aaron Navalaka, Sean O'Connell, and Wasif Kamal, and we are Project Icarus. To the right, you can see a picture of our prototype, and the agenda for this meeting will consist of Wasif telling you about our motivations as a team, as well as specifications of our product. Jerome will follow and share how we performed on the wind and laser tests completed during the semester. Matt E will speak in detail about the key features of our product, while Matt L will talk about the design evolution throughout the past few months. Sean will end with some cost information and Aaron with the summary.
For our Hedgehog concept, we wanted to do something we were passionate about and would set ourselves apart from already existing small-scale heliostats on the market. So our goal was to make the most economic and the most simplistic design we could. We generated a design that was easy to manufacture, assemble, and maintain by using primarily 3D printed parts without needing any complex parts like bolts or bearings or gear trains. Using simple 3D printed parts, we eliminated otherwise large material and part cost, made it so that parts can be easily remade and replaced if the need arises, and achieved high solar tracking accuracy. The cheapness and simplicity of our design allow several modules to be assembled together to maximize solar capture. For some of our key specifications, when switched into the safety mode, the heliostat has a max volume of 6 by 8.8 by 10 inches cubed. A single module has a mirror coverage of 6 by 6 inches squared. The heliostat is actuated using NEMA 17 stepper motors with a 1:5 gear ratio and a step size of 1.8 degrees. This gives our module a range of 300 degrees in the azimuthal direction and 180 in the elevation direction. Commands are communicated to the motors using a ESP32 microcontroller with an SHT C3 temperature and humidity sensor.
During the course of this semester, we subjected our prototype to a number of tests. The first of these was a wind survivability test that occurred in 2 stages, a low-speed stage and a high-speed stage. The low-speed stage occurred at, we put our device in a wind tunnel, and while it was rotating, we exposed it to about a wind speed of about 5.3 meters per second, which is approximately twice the average wind speed in Las Vegas, where these prototypes are intended to be installed. For the high-speed test, we subjected it to a similar procedure. Instead, this time it was about 60 meters per second, which is about twice the maximum speed recorded in Las Vegas, so adding a double factor of safety there. Now, initially, when we ran this prototype presented in this image here, it succeeded in the low-speed test, but had a catastrophic failure at the high-speed test. Wind came under the lower container there, the one in red, and lifted it off the base, causing our heliostat to essentially fall apart. So, in order to fix this, we modified the base somewhat. As you can see here, we added large extended posts that covered the prongs here on the lower casing, and we added a rail to seal that gap where wind could enter in, which resulted in a successful test at the high speed, which you can see here. In the high-speed test, our prototype was kept in a safety configuration, so not the actual performance, but in cases of high speed, our prototype would lock down and perform like this, which does not fail. Our secondary test occurred later in the semester, a laser reflection targeting test, though of course this test actually tested a bunch of various skills of our prototype. Whether it was modular, how they're connected with the quick release coupling installed at the bottom here, whether it displayed the full range of motion that we intended, whether it responded to the coding commands that we had programmed, whether it was able to home, whether it was able to go into the safety mode when we commanded it, power down when we commanded it, whether it was able to accurately detect temperature and humidity. When it came to the actual targeting of the laser, as you can see here, there were 3 main types of tests that we did. The first were manual targeting, whether we could physically aim the heliostat at any target we desired. The second is we were provided with a set of coordinates and then asked to hit a necessary target. That is the test you can see here. And the final test would be we were hit a target manually and then reported back the coordinates to determine whether they corresponded actually. We are pleased to mention that the heliostat performed most of these tests with some slight variation in our reported coordinates compared to the actual coordinates. And here you can see our successful test.
All right, I'll go into a little bit about some of our design highlights and key features. So on the right here, you can see an exploded view of the assembly of our design. And this will sort of illustrate the ease of assembly aspect and the simplicity of our design. So one of the notable things is we really don't use any fasteners when it comes to our design in terms of assembly. The one exception in this prototyping phase is the heat set insert that is used to fasten the prototype to the quick release coupling. That was simply an artifact of our testing setup. That would not necessarily need to be implemented in a production design. So that's one thing, that there's no fasteners. How we do fasten things together, one of the ways is through tight clearance fits. So a lot of the holes and shafts were basically experimentally printed in an iterative fashion until we got the correct fit so that they could still function properly, but stay together and not be able to move with respect to each other in ways that weren't intended. So through those tight clearance fits, a lot of those holes and shafts were able to fit together. We also used rail and channel fits. For an example, the top gear casing and the actual tower of the heliostat. On one side, there is a rail 3D printed into it, and on the other side, there's a channel. So when the heliostat is assembled and that casing is put on, the rail is simply slid into the channel to fasten it properly and to hold it. And this fit was tested in the wind testing test, and it held up under the conditions. The other fastening mechanism is snap fits. You can see this in the bottom gear casing that goes around the base plate. So you can see there's two halves down there, and there's actually snap fits on the half on the right. So these parts are simply brought together over the base plate. The snap fits fasten in, and again, it's very tight enough so that it can survive the wind or any other conditions that would be provided, protect the electronics inside. If we need to take off the snap fits, you could just use a small tool like a screwdriver, push in the actual fits, and then you can release it. Another important aspect of our design is actually the environmental casings. We understand our prototype, or the heliostat as a whole for production, I guess, is supposed to be used in the Las Vegas environment. So it's going to be a desert environment. There's going to be a lot of wind and dust and debris. We understand this can be dangerous for things like the gear trains and electronics that can't really afford to have those debris, that debris get inside of it. So we designed these casings to go around those components and protect them, as well as to hold certain components together, because again, we're not using fasteners. So the two images on the left, the upper and lower left, those are the top gear casings. So the lower left one slides on top of the top gear train, and then the upper left one just clips onto the bottom to protect any dust or sand or anything from getting inside. It also holds the gear train in place. The upper middle and lower right images are again of that bottom gear casing. That is used to protect the base plate and everything inside. So there's a motor in there, there's the lower gear train, basically protects all of that from debris, and also helps to hold the tower in place. Then finally, in the upper right, we can see a motor casing there. That's for the motor that powers the upper gear train. So again, that simply slides over it. It holds the motor in place and prevents it from sliding out, as well as protects those electronics from the environment. Next, it's notable to talk about our homing algorithm, specifically the mechanical aspect of it, which is the limit switches. The limit switches are important, and homing as a whole is important so that we can get accurate angular measurements every time we restart the heliostat, so we're going from a consistent reference point. So basically, we have two limit switches, and they're independent of each other. So the elevation and azimuth are homed completely independently. So if troubleshooting is necessary and there's error in one of them, we can basically separate them so the systems aren't coupled and it's easier for troubleshooting, things like that. On the upper two pictures, you can see the limit switch for homing of the elevation. So that one is on the top gear casing. Basically, the way that one works, the arm that holds the mirror will spin down until that arm basically touches the limit switch, and then it uses that as a reference point. Then on the bottom two pictures, you can see our azimuth homing limit switch. That limit switch is on the base plate, and the tower that basically spins for the azimuth, that has a little fin on it, and it'll touch that limit switch as it spins in the azimuth to get a reference there. It's notable with regard to our algorithm that when we approach the limit switch, we use the smallest step possible so as to get a consistent homing location and a consistent reference point, regardless of when we're homing, so that we can get consistent angular measurements at all times. Now to talk about our gear trains. So again, like the limit switches, the two gear trains are independent. One is for azimuth, one is elevation. That's helpful also for the kinematics, in terms of the inverse kinematics, being able to figure out those two angles independently. But so simplicity in that case. Also simplicity in the design itself. You can see both designs are exactly the same, just a configuration of two spur gears. It's a very simple gear train. The larger one is 50 tooth, the smaller one is 10 tooth. It's a 5-to-1 gear ratio with the smaller gear driving the larger gear. That allows us to bring our resolution down to about 0.36 degrees. So our requirement for the project was 0.5 degrees, was actually the minimum resolution, but we understood that there would be some non-idealities in terms of slipping, maybe some wiggle room in between the gears. So we used 0.36 degrees to sort of put in a factor of safety there. Now to discuss the manufacturing and the geometries of the parts in general. First of all, it's notable with the material that all of the non-electronic parts are 3D printed. So everything except like motors and limit switches and wiring and that sort of thing. It's all 3D printed. The main advantage of this is the ability to simply print complex geometries. You can see this with the left and upper pictures. These are sorts of geometries that would be very difficult to manufacture through traditional machining methods. They might require complex CNCing or something else entirely. But with 3D printing, we can quite easily manufacture these components. Being able to manufacture complex geometries allows us to have one part that can perform multiple functions due to this complexity. We can take, for example, the picture on the left with that tower there. So you notice the bottom of it is a gear. So it's part of the bottom gear train that moves the azimuth direction. But also as you go farther up the tower, there's a square indentation, and that's where the motor goes that actually powers the elevation motion. So this single part actually has multiple functionalities. It's able to do that due to the complex geometry that we're able to create through 3D printing. Additionally, another advantage to it is simply with rapid prototyping in this stage, and then rapid replacement in the future when it's time for further testing and even some implementation. 3D printing allows basically for parts to be rapidly made and modified to actually optimize the design and replace and repair components if necessary. So now I'd like to talk about our power transmission from the motors to the actual angle movements. So in all of our power transmission, we use D shafts power transmission. We started by looking at the motors. The shaft themselves are a D shaft. So there were several ways to go about this. One of the traditional ways would have been to use a set screw to cause the two parts not to rotate with respect to each other. We didn't really like this idea because, again, one of our design goals, our main one is simplicity, and that would add a fastener, which is another part, increased complexity in some sense. So what we actually did is we took the small gears that mate to the motors, and we actually printed a D shaft hole inside of them that would fit in to the motor shaft. So that would cause them to spin together in the rotational direction. And then we also experimentally worked on making that fit tight enough so that the gear wouldn't move axially out of the motor. So that was again through rapid prototyping through 3D printing. The D shaft is a simple geometry that through these manufacturing methods is very easy to accomplish. Even in the upper right image, you can see there's a power transmission there that's not even related to the motor itself. It's between the gear train and the upper arm that holds the mirror. We still use the D shaft power transmission there because it was just such an ease of implementation for that.
So now I'm going to talk about some of the things that changed throughout the semester with our design. First off, the probably most significant was we upgraded our gear ratio from 4 to 5. This is calculated using the equation shown. And initially we wanted to do a 10 tooth with a 40 tooth. Considering our motor had 1.8 degrees per step, this would have allowed our model to have 0.45 degrees per step, which yes, is within the allowed tolerance, but we suspected due to the fact that we're 3D printing our gears and other losses that it would actually end up being greater than the 0.5 degrees that we needed. So we upgraded that to a 1 to 5 gear ratio, giving us 0.36 degrees, which is more within the tolerance. Now I'm talking a little about the casing and the base. As we talked about earlier, we were not super successful with the high-speed wind test early on, so we made some modifications. These consisted mostly of putting this ring around the outside of the base. This prevented wind from coming in underneath and lifting the casing off of the base. In addition, we added 4 posts in the corner to support the casing. And most importantly, we put a ridge in these front 2 posts so that when the casing slides on, it cannot be removed vertically. It has to be slid out. Also, our casing has these snap fits. Originally, these snap fits were not super easy to work with, but through some testing and through some iterations, we actually were able to get very easy to use ones that also had a very sturdy fit. Moving forward, when we designed this, we initially thought down here in the bottom left picture that a shaft collar was going to need to be put on this gear shaft. We spent many hours testing, and through a lot of time, we came to the conclusion that with our fits and our tolerances, that gear shaft was not going to slide out. So we actually scrapped the shaft collar, and in order to save money and increase simplicity. As I was talking about with all those hours of testing, in this bottom right picture, you can see that there's 2 heat sinks on the motor drivers. Originally, we didn't have that, and these motor drivers would overheat very aggressively as we were testing, and that would cause the system to kind of go haywire and not function correctly. So we added these heat sinks in order to cool off the motor drivers and allow us to test more efficiently. So now I'm going to talk some of our rapid prototyping. Rather than printing a bunch of different bases and putting different heat set inserts in there, we decided to print a test block and put a bunch of different hole sizes. So these holes have different diameters and different tapers. And to test them out in order to determine which is best for our heat set insert. After we did that, we implemented it into our base design and never had any issues with it. Moving to the center picture, this was how we rapid prototyped the different diameters and distances between the gears, considering our elevation and azimuth have the same gear ratios. The distance between was pretty similar. So this was used because it took probably about 30 minutes to print each one of these, while if we wanted to print an entire base plate, it would take well over 12 hours. So this allowed us to rapid prototype our base plate and to tolerance those holes. And a very similar process was done for the elevation direction in order to save time and efficiently determine our different sizes for those holes and spacing between. Finally, on the right-hand side is the upper arm. This is what meets with the gear shaft and goes and holds the mirror. We noticed that this had some play with the gear shaft. So this was rapid prototyped by the right picture. We were able to print this over and over again in order to get the correct dimensions rather than having to print the entire upper arm.
Next, we'll talk about some of the costs that it took to design the heliostat. On the left, you can see the base cost that it takes to design a heliostat in general. To name a couple key items, this includes the DC power supply, 2 motor drivers, 2 stepper motors, breadboard, sensors, switches, the microcontroller, and the heat set insert screw, totaling out to $151.14. On the right, you can see the design unique costs. We only had one design unique cost since all of our parts were printed by PLA plastic. The PLA polymer is priced at $29.99 per kilogram, and we used a total of 1.34 kilograms, including all of the support material it took to make each part. This comes out to a total cost of $40.30 for our unique design. Together, this comes out to a cost to build one prototype of $191.44. And when you go on to build one unit within a production of 3,000 units, that cost comes down to $155.72, since you do not need to purchase another quick release coupling and heat set insert screw. Value engineering can reduce production costs, and our team recommends that manufacturers employ injection molding, draw up contracts for wholesale pricing, and eliminate unnecessary parts and geometries. On the right is a summary of the cost it would take to employ injection molding. And the key takeaway from here is the material costs range anywhere from $1 to $5 per kilogram, as opposed to the $29.99 per kilogram of PLA. That $1 to $5 is thermoplastic pellets used for injection molds.
So just to summarize our design, we believe that our design should be selected for further development because of its simplistic design. As stated earlier, um, the design, most of the parts are 3D printed and it can be easily assembled while still be able to complete certain tasks and requirements such as the wind survivability test and the laser reflection test. In addition to that, the directional movement of the heliostat is uncoupled, meaning each movement, the azimuth and elevation, does not interfere with each other unlike other heliostat designs. And with all these in mind, the heliostat design is still way below the given budget, therefore allowing for further development and either adding complexity or more components to the design.
We have reached the end of the presentation of our simple design. I'd like to thank our sponsors and you present here for coming and listening. We'd be happy to answer any questions you may have with the time we have left.
Cool. All right. So we've had Devangi with us for a little while, and then I'm imagining that Jave is Javian, who popped in a couple slides from the end. So if you guys, DG or Javian, have questions, feel free to jump in with those. Can you guys go to slide 16? There's something that wasn't clear. Oh, yeah, there you go. Okay, so what's the column for aluminum in the table in the bottom middle of the screen?
Yeah, so these are basically two types of injection moldings. And so you could see the production volume for if you were to make a plastic 3D printed mold, it would only be useful for about 100 units at a time. But if you were to invest a little more and go for an aluminum cast mold, then that would produce about 5,000 units. So that's just where the discrepancy is. And you can see the difference in the fixed cost of purchasing, or rather producing the 3D printed mold and outsourcing that aluminum mold.
Got it. Okay. You can get a 3D printed mold for injection molding? Is that a thing?
You can make one in-house yourself, yes.
Out of what material?
Thermoplastic, ABS plastic, any kind of plastic that you feel would do you justice.
That's exciting. I hadn't even thought of that. Because so normally, well, I mean, you guys have taken the manufacturing course. Okay.
Yes.
Hopefully by now.
Yeah.
Yeah, and I'm not sure. Usually it's Hitomi Greenslet who teaches that, although some other faculty do too. Injection molding is usually, as you've described, it's a mold made out of metal, and you inject high temperature plastic into the metal mold. So that's pretty interesting that you could 3D print a mold. You'd have to 3D print it out of a material whose melting temperature is substantially higher than whatever plastic you're using to make the actual parts out of.
Correct.
And clearly it doesn't last nearly as long, right? You're 100 units and your 3D printed mold is toast.
Right. That's the trade-off where, if we were producing 3,000 units, it might be smarter to go with an aluminum mold anyways, but it depends on how many units you're putting out per year.
Yeah. Wow. Okay. Well, what a fascinating modern age we live in. There's a whole manufacturing technique that I've never heard of before. So that's cool. Well, good. Did you guys find that somewhere, or did you know about it in advance from like an internship or from the manufacturing class?
No, we just looked for it for anything that could reduce costs, and we were surprised to come across that as well.
Yeah, not me too. I didn't even know that was a thing. So wow, neat. Okay. Oh, okay. And Alex just jumped in as well. So we've got at least a little bit of a semblance of a panel here. So what's today? Today's the 19th. So in 3 weeks? Yeah, 3 weeks. We're teaching Mech 3 all over again from the start. However, those guys in the summer are going to have the benefit of your designs, and we're going to ask them to not just build a heliostat for a lab environment that redirects laser beams, but to take your designs and harden them for operation outside and redirecting sunlight. So Sheffy said that if we can aim sunlight at like 2x4s that we mount in the ground and get the 2x4s to catch on fire by the end of summer, he's going to be happy. That's his end goal for us. So having gone through this process of taking a paper design to a functional prototype, if you guys were the instructors of Mech 3 for the summer, what would you tell those guys? What wisdom would you impart on them from your experience in this class?
Start early. Don't procrastinate. I mean, that's just general advice, but especially true in this case. I would say that we were mostly on top of it schedule wise during the week, but we did spend a lot of time closer to the end of deadlines than we probably should have.
Another thing regarding prototyping, to do small scale prototyping when thinking of making design changes, like Matt had described earlier, when we wanted to change like the fits between shaft and holes, we didn't reprint the entire part. We manufactured a small sort of simulation of that hole in that shaft and kept iteratively manufacturing those small scale versions to see which one fit the best. So that can help when making design changes and stuff, instead of having to manufacture the entire part again, which I understand would probably be even more complex since they're making more hardened designs now, more fleshed out.
Yeah, kind of going off what he was saying, something it took me a while to learn was the fact that depending on the thickness of the plastic, when you 3D print stuff, it actually cools and shrinks and like changes shape differently. So talking about like when I was doing the holes and the diameters for the base, that model didn't actually cool the same as our base did. So there was a little bit of a learning curve along with that. But that was something I didn't even think of, was the cooling of different, the plastic in different shapes and how that works. So that's a thing to keep in mind when rapid prototyping.
Great. Yeah. So you guys are discovering that there's sort of a this class, Mech 3, was not a required class to graduate with a UF mechanical engineering degree as recently as 2019. There's they changed the curriculum, and there was a bunch of students that were under an old catalog that were grandfathered in, and you guys are really sort of the first, maybe the second cohort that's had to come through and take this as a required class. But you're getting a sense, I think, at least based on those answers, that there's a lot of kind of unwritten, unspoken knowledge and expertise that you pick up as you're prototyping, right? All this and this is part of the, everybody is kind of bemoaning the loss of manufacturing capability in the US as manufacturing jobs are sent overseas where labor is cheaper. So in addition to jobs going away, we're also losing, a lot of that just sort of practical hands-on know-how. And the thing that, and you guys sort of alluded to it with some of your comments about, you got to worry about shrinkage and print out just one little small element of a part when you're trying to test things like fit and tolerances and so forth. The image that you guys presented to me that was the most sort of interesting and impressive was the one where you had all those different holes and then the heat set inserts, the threaded inserts. Yeah, there you go. Right. So you guys basically ran an experiment, right? It's you probably went and tried to look up, somewhere online, and you found a bunch of Reddit pages and Wikipedia pages and a bunch of random stuff about what the right hole size is for the heat set inserts. But the power of 3D printing and rapid prototyping is you guys could actually run this experiment and determine for yourselves what the right hole size for a particular heat set insert is. And that, interestingly, when talking about intellectual property in Mech 2, that becomes a trade secret, right? So that's something that you guys know about how to fabricate your particular heliostat, that if this weren't a class and you guys weren't graduating or going off to doing what, if we were starting a company, right, this is information that you would not share externally, right? This is something that you would keep close internally to the company, because it prevents other competing companies from manufacturing heliostats with the same quality as you guys are able to do, because you've got this knowledge that other companies don't have about the appropriate hole size for heat set inserts. So I'm wondering, like, what other experiments did you guys run, like where you did the engineering calculation and it kind of didn't give you the right answer, and then you had to actually 3D print and run an experiment to prove to yourselves that a particular design would work or was best? Are there other examples that you can think of?
In terms of experimentation where we specifically 3D printed stuff, I believe what we've shown here is the vast majority of it. However, we did do quite a large amount of experimentation when it came to our code. We did have to vary that a lot. We experimented with different sorts of things. I believe the vast majority of time we spent in lab was just refining our code and the various parameters associated with that in order to accurately pass the laser test.
To talk a little bit more on that, kind of going back to fits and things. So I know Matt talked a lot about the fits of the gears and the D shafts of the motors. That was and the D shafts of the upper arm, as shown here on the right, with the gear shaft. A lot of that was interesting because it wasn't necessarily just hole diameters. So like you can get the hole diameters to be good, but when it's a D shaft, you also have that flat piece. So I would say there was a decent amount of experimentation there between different diameters and different flat side lengths, because there's two things that kind of control it. So I'd say we did experiment with that a good bit.
Good. Okay. Before I ask my next question, DG, JV, and Alex, do you guys have anything you want to ask?
Not really. I kind of got here late, so I'm gonna here for all this.
I had one question which they touched upon, so I'm good.
Okay. Well then, so my last question is, tell me about your regrets. And I'm thinking all the way back to the beginning when you guys did the House of Quality down selection and you picked whatever your base inspirational design was. Do you regret that decision? Did you make a bad choice? If you knew then what you know now, would you have selected a different heliostat to start with, or did you make a good decision?
I have one primary thing that I would have changed, which is a decision we made early on. It was the length of, I guess, the arm that the mirror extended from. So sort of that moment arm there that was rotating. After testing and things and making the kinematic model, yeah, we realized that it would have been a lot simpler if we had made the axis of rotations, both axes of rotation, intersect with the point of reflection on the mirror, instead of having that arm that rotates with respect to everything, sort of. Then changes in elevation would basically move that arm as a whole and basically complicate the kinematic model. Whereas if the reflection point was at the axis of rotation, the kinematic model would have been much simpler. Everything would have rotated around that point.
I personally think we could have leaned a bit more into, I know we do have a lot of fillets in our design, as we leaned into 3D printed geometries that can really only be made with that. But I believe that there are some locations, especially on the gear shafts and whatnot, where fillets would have helped a lot more. Some of our earlier models had structural integrity issues that we did end up fixing, but I believe fillets would have solved those issues faster.
Yeah, if Tom Singer from Northrop Grumman were here, he would agree. He's been admonishing groups all day. I'm sad he's not here about stress concentrations and needed to add fillets into square corners and stuff. So good observation. Okay, well, it's about 5:23. So if DG or Javian or Alex, if you guys don't have anything else, I'll probably just wrap it up there. Anything else that you guys wanted to comment on while I've got the recording going?
Just a last thank you.
Oh yeah. Oh no, this was fun. We've you know, there was a moment which was you know, now talking about regrets. One of my deep regrets is fall 2020. I in summer 2020 I taught Mech 2, and it was the best Mech 2 class that I've taught. And I thought, oh, I've got this class totally dialed in now, and this is exactly how I'm going to teach it from here on out, and it's going to be perfect, and there's going to be no more complaints. And then fall 2020 hit, and yeah, DG is saying our semester, and fall 2020 hit, and it was a disaster. It was probably the hardest semester that I've had at UF. This class, you guys, like, was yeah, not our semesters as DG with respect to fall 2020. This whole semester with this class was amazing, right? I felt like everybody was really engaged and challenged. This was a hard problem, but it wasn't so hard that it was like impossible and people sort of lost hope. I think if any of you guys survived the microbioreactor for Mech 2, that was a project that was way too hard. And there was a lot of students that were very unhappy at the end of the semester because we just asked too much. But this one was just right. And just the chemistry and camaraderie of the class and, you know, this group made this semester a lot of fun to teach and kind of watch you guys fight your way through. And I think in the end, almost every group was successful in at least you know, some measure in terms of the laser targeting test. You know, not every group got in the yellow for every single test, but you know, you guys are all able to redirect the laser in more or less the right direction. So I think, you know, just more experiments and more refinement and stuff, and every single one of these heliostats, I think would be viable candidates for the next stage, which is small batch manufacturing. That we're going to do in the summer. So yeah, I appreciate your thanks, but I also want to thank you guys for, you know, making this semester, you know, just really, really fun. And you brought a lot of positive energy and creativity. And this is exactly what Capstone should be. So I appreciate that.
Thank you. Means a lot.
Very good. Okay. Well, let me stop recording.